Good afternoon, everyone. I'm Yitong Dai and came from Xi'an Jiaotong University. And it's my honor to be here and introduce our work, Dependency Facade Coupling and Conflicts between Android Framework and its customization. First, I will introduce our motivation. As we all know, mobile device manufacturers developed their custom Android OS, which termed the downstream, based on the Google Android, which termed the upstream, to support new features. And during their daily independent development, the downstream also periodically merged change of a new release from the upstream into its development branches, keeping in sync with the upstream. Due to a large number of commits to be merged, heavy code conflicts would be reported if auto-merge operation failed. So prior work has studied conflicts due to the merging of the upstream and downstream. Furthermore, the downstream contains 4 kinds of entity. First is ventures extension entities that are created by the downstream and the upstream development is imperceptible of them. Then is a native entity, which are native entities keep unchanged in the downstream. And also it has some intrusively native entities which are originally created by the upstream, were further modified by the downstream. Also, it has some obsoletely native entities which are created by the upstream. Earlier versions were deprecated by the current upstream version. However, such obsolete upstream entities are still reused by the downstream. But it's still unclear about the coupling between the downstream and the upstream, which we termed this coupling as the dependency facade, as well as how merge conflicts are related to this coupling. Then is our main methodology. To address this issue, we first proposed the dependency DeepFCD to reveal the dependency facade from 3 aspects, including interface-level dependencies, intrusion-level dependencies, and dependency constraints, which is imposed by the upstream non-SDK restrictions. So first, we use Array to produce dependency graphs, as shown in Fig A. Each node denotes an entity E in source code, such as classes, interface, and each directed edge denotes a dependency between entities, such as inherent between classes and call between methods. Then, for entity ownership and intrusive operation identifications, we first leverage the comment like git blame to obtain the commit site of the entities and find the intersection between this commit site and different commit history which came from the downstream, the corresponding upstream, or the older versions to identify entities ownership, as shown in Fig B. Moreover, we combine the dependency graph analysis, the reflective manner, and the git blame results to detect various modification operations to identify these modifications made by the downstream development to intrusively native entities. Also, we decompose the dependency graph of the downstream project to localize the dependency facade, a minimal subgraph that couples a downstream code with the upstream one. And the third is a dependency constraint imposed by the upstream non-SDK restriction. Non-SDK restriction imposed, which is proposed by the Google, indicate that some APIs is in the upstream code might be unstable and frequently updated by the upstream. This module will label the entity node with a restriction level attribute for the upstream and downstream dependency graph, as shown in Fig C. And then we get the updated graph both in downstream and in the dependency facade. Before our implementation of our experiment, and let me introduce our experiment setup. We will study 4 research questions to demystify the dependencies between downstream Android customizations and the Android framework on which the customizations are developed. The first question is, how do the downstream customizations rely on the upstream Android through interface-level dependencies? With a clear design boundary indicated by the interface-level dependencies, the downstream can easily involve with upstream. The question 2 is, how do the downstream customizations rely on the upstream Android through intrusion-level dependencies, which made the fine-grained implementation logic of the downstream mixed together with the upstream? It would blur the design boundary. And question 3 is, how do the downstream customizations adapt to the dependency constraint imposed by the upstream Android? This study will explore how the dependency restriction evolution in the downstream project is constant with that in the upstream Android and how downstream projects follow the dependency constraint on the dependency facade. And the final question is, how do merge conflicts occur on the dependency facade between downstream customizations and the upstream Android? A merge conflict would be incurred when the downstream merges the update from the upstream. So our interest is the textual conflicts reported by the version control system, since their resolution is a high priority to make the updated OS quick to run, facilitate subsequent functional testing. And finally, our study collect the dataset totally with 15 downstream versions, 15 upstream versions, and 122 million lines of code and 16 million common items. Especially, we also collected an industrial project anonymously named Industrial X from an industrial well-known provider of smart devices. The industrial venture has maintained its Industrial X for 10 years. It takes the top 3 in domestic market share. And that is our experimental results. So for research, for question 1, we first observe interface-level dependencies in the dependency facade as shown in Table 2. We found that downstream development consider aggregate in priority to exploit upstream entity rather than implementation and inherent. And also the downstream development employs Java inflection to access the property of upstream entity at runtime. And then we use some calculation to calculate the size of dependency facade and the proportion of the entities with different ownership in the downstream dependency graph. We found that industrial projects exploded 13.5 times larger dependency facade than that of open source projects. And among code entities in downstream project, actively native entities account for the most. And for the research question 2, we first observed diverse intrusive operations made by downstream projects to the upstream. And we found among the method block modifications, modified method body takes the most cases. And one frequent change is that the downstream development defines new condition branches inside the method. And regarding modified accessibility, we found that the downstream development tend to promote accessibility and remove the final keyword. And then in Fig 5 shows the downstream directly replaces the base class of the native class with extensive one. Such a change deepens the design hierarchy of the upstream. Consequently, the downstream would have to continue modifying other upstream entities influenced by these base classes. And downstream, we also find that we analyze the reverse dependencies, the dependencies from the upstream to the downstream entities due to intrusive modifications. We find that inherent and implement reverse dependencies rarely happen except a few cases. Their usage deepened the dependency hierarchy or even broke the design hierarchy originally created by the upstream. And for the research question 3, the restriction level of non-SDK entities can be claimed as several kinds. SDK which can be publicly accessed, blocked which should not be accessed, and unsupported, which can be exploited by developers, would be changed in the future, and max target X, which can be accessed in the Android versions no later than X. And we first employed a state transform graph to model restriction level change of API entities as shown in Fig 7. We found most of newly added API are blocked. There exists change of unsupported to max target X and blocked to SDK. And we also find the change of SDK to blocked uniquely exists in the industrial projects. And we further examined the restriction level change of upstream Android API entities made by downstream. And Figure 8 depicts the restriction level change to upstream API entities made by the downstream. And we found no change had been made by the open source project, and on the contrary, both restriction enhancement and restriction loosening exist in the industrial X. Besides, we compute the PS that measures to what extent the downstream API entities call the block, unsupported, and SDK upstream entities on the dependency facade. Among those entities, we further accessed the PI, the proportion of intrusively native upstream non-SDK entities that were modified by downstream projects. And we found that downstream tend to rely on SDK API as well as a small portion of block API. A larger portion of upstream block API are on the dependency facade are further modified by the downstream. And for the final question, we randomly sampled 300 conflict blocks in NUM for manual analysis to understand how dependency facade would be involved in merge conflicts. Based on those conflict files, we found merge conflicts are frequently caused by downstream change of upstream entities, such as method block, add class field, and add important statement. And then we also find reverse dependencies like call inherent implement due to intrusive change are involved in code conflicts. And merge conflicts also occurred in non-SDK API chains which are related to dependency constraints. And finally, it's our conclusion. We suggest that the downstream development should monitor the dependency facade change to be a clear design, facilitating the prevention of merge conflicts, and also they should detect dependency restriction violations during the development. And finally, our work focuses on the dependency facade that couples the downstream projects with the upstream Android. And we suggest that the downstream projects should monitor the change in the dependency facade and the violations of dependency constraint, thus helping mitigate the potential merge conflicts. That's all, thanks. And is there any questions?
Well, let's thank the speaker, Utting. So if there is any in the audience that has a question, I would be, running over there to get it. Okay, maybe after lunchtime, there is not much energy for it. So I would have a very general question. Usually studies are done, you have done a qualitative evaluation, you have done a quantitative evaluation, and you have shown that the problem is quite important, quite relevant. It happens very often. What would be the next step for you on a practical level? You have shown the potential of your tool. You are going to integrate your components somehow in the Android framework, or you are going to just validate with developers your tool. What is the next step from your point of view? Going more on a practical adoption, if possible.
We actually do some further research after we publish this, after we handle this paper, and we find some module that the downstream developers couples the upstream one, and they have some anti-patterns in this dependency facade, and we classify them and search them in our dependency facade, and we find some they have some characters in common, and we now take some experiment on them and try to outcome some some anti-patterns and some other suggestions for this scenario like that.
Okay, thank you. I don't feel that I'm alone. I'm just reading, and people are reading your answer. If there is no other question so far, I will thank again the speaker, and then we go for the next.
Okay, thank you.
Thank you. Thank you.
This is going to be a little story about a system that you've probably never heard of, but it actually is a really important system. It's called Monty. It's a system that was developed and maintained by NASA for 20 years, and they call it Google Maps to the solar system. So if you are sending a mission to somewhere remote in the solar system, to properly operate this mission, to track it, you need to understand the map, the 3D map of space. The Monty system provides this mapping capability for NASA, and it is currently responsible for the tracking of about 18 projects, and one of those is a future planned human mission to Mars. And because there's humans involved, this is now considered a safety critical application. This system, as I say, has been developed and maintained for over 20 years, and it has hundreds of C++ and Python applications. They add about 30,000 new lines of code per year. They get about 150 bug reports and about 150 feature requests per year. So this is a large, active system, 800,000 lines of code. And NASA has a policy that they want to, for safety critical systems, as you'll see in a minute, that they want to ensure that the systems have appropriately managed, mitigated risks. So what we did is collect data on each of the files in the system. How big is the file? Its lines of code, the cyclomatic complexity of each file, how many defects that file suffered over the time period, and how much effort it took to remove those defects. And NASA has two maintenance risk concerns. Of course, they're concerned with how defect prone a particular file is. The more defect prone it is, the more effort you would want to put into analyzing, testing, code reviews, whatever you can do to minimize those bugs, to minimize the risk. So bugs are going to happen, and you want to figure out, ideally, before they happen or before too many of them happen, where to put your effort to try and minimize or mitigate the risk. And when they do happen, you've got to figure out, well, what do we need to do to repair those bugs? What can we do to make sure that the system is in full operational good health? Do we have enough staff with the right capabilities, with the right experience to analyze and debug those? Is the risk of a defect low? And so there's this program that NASA has instituted to measure maintenance risk. And right now, a lot of maintenance risk is done by looking at lines of code. Big files are bad, right? We all know this. But there's a problem with just looking at lines of code. Yes, it's true that big files are bad, but there's other factors that are also important and more insightful. So churn, how quickly is this file changing? How often is it changing? How many new lines of code are added to it in a given time period? How complex is this file? What's the capabilities of the staff, and are they already overloaded with work? There are predictive models of maintenance based on code size, but while this might be useful for planning your staffing, right? If our code base is expected to double, we need twice as many people, twice as many programmers and maintainers. It doesn't really tell you what to do to manage risk. So if I have a file that's 10,000 lines of code, I cannot divide it up into two 5,000 line of code files and cut the risk in half, right? It doesn't work that way. So it's not a very actionable measure. NASA has this policy, which you probably can't read, but it basically says that if a project has safety critical files, and the Monty project does, then the cyclomatic complexity of those files, the code complexity, has to be 15 or less. And Monty is safety critical software, and therefore it has to comply with this NASA policy, or you have to apply for and justify a waiver from this policy, why you cannot make your code less complex. And so the Monty project, having to comply with this policy because it was designated a safety critical system, they wanted to understand, well, where does this magic number of 15 come from? And is it the right number? And in fact, the team didn't have any experience with complexity measures before this, and so it seems like a reasonable question. Why this magic number 15? So the team decided to embark on an empirical investigation to try and understand this. So there were 3 research questions. The first is, if we comply with this magic number, will it actually reduce risk? That seems like a reasonable thing to understand. And if it does reduce risk, well, how much? Right? How big an impact does this have? And is this a good threshold? Maybe the number should be 10. Maybe the number should be 40. Right? Why 15? So to investigate this, the team mined the Monty repository, and when I say the team, it wasn't me. There were other people that did all the real work. And they looked at the code, and they looked at the Bugzilla repository, so they would understand what was a bug and when it happened and which team it was associated with. And by looking at the code repository and all the commits, they could understand which commits were made to resolve which bugs and how many lines of code those were. Okay. So let's take a look at the 3 research questions. I'm not going to go into great detail on the analysis. You can read the paper just to give you the highlights. Looking at defect proneness, it turns out that cyclomatic complexity is highly correlated with defects. So it is true that a higher CC number, cyclomatic complexity number, means higher numbers of bugs. And it also is strongly positively correlated with effort, right? So that's a good thing. That means that somehow, somewhere, this complexity measure is predicting what we want to know, that a higher number means a worse thing, and therefore we should pay attention to it. Also, and this is really important, that not only is it a reliable predictor, but it's different than SLOC, lines of code, because this is actionable. I may not know how to make a file smaller, but there are established refactoring techniques for reducing the complexity of code. So I can reduce the CC score. Pretty graphs, you probably can't read those again, but they're in the paper. But just to give you the intuition, how much does conformance to this number, this magic number of below 16, reduce risk? So if you look at mean defects and mean effort, the top 2 graphs, what you see is that there's a knee in the curve at somewhere between 10 and 20 for defects and around, 20 for expected repair effort. So that says that there's something interesting going on when we get above 20. In addition, what's the variability? So there's also this interesting knee in the curve, and what you can see is as the complexity numbers increase, there's an inflection point. Beyond that, the variability grows huge. So that means if we keep things to the left side of that inflection point, the smaller complexity numbers, not only are there fewer defects and less effort, but the variability is less. It's more predictable. Third research question. If we keep the CC under 16, do good things happen? Is this really a good thing to do? So again, you can see in this distribution, and there's another graph that shows this in the paper, that there are basically these two distinct groups of high and low CC, and they correspond to high and low numbers of defects. And it turns out that a CC number of around 7 is the optimal separator. That's what separates the low defect group from the high defect group. If you look at effort, again, there's distinct high and low effort groups, and there the CC separator is around 25. 7 and 25. Anyone notice anything interesting about those two numbers? The average is 16. Somebody thought about this, or they got lucky. But it turns out that this seemingly arbitrary number in the NASA policy is in fact strongly empirically supported by the data. And it does seem like a perfect compromise between defect proneness, reducing defect proneness, or controlling defect proneness, not reducing, and controlling the amount of effort required to repair those defects. So to summarize, this policy was just a policy, and it was accepted initially on faith. It seemed like this couldn't possibly work. It was very crude, just this arbitrary number, but it turns out that it actually is a really prudent number. Maybe they just got lucky, or maybe they had done some analysis that we were unaware of. But there was no analysis, there was no empirical support given for this number. It was just the policy. And the project has since adjusted its practices to report files with a higher complexity of 15 and to do something about the files that are higher, either refactor them or to do additional mitigation strategies like higher efforts of quality assurance. So this turned out to be a really useful investigation in terms of providing actionable directives for this important software project. How am I doing for time? Okay, yeah, I'm finishing up. So there's a set of research challenges. You can read more about those in the paper. I think one of them is the second bullet. Do these results generalize? This is a good number for Monty. What's the good number for your system? But there's a really simple way of following the same methodology to figure out what that number should be for the system. So at this point, I'm happy to take any questions. I don't know, is Dan Port on the Zoom call? Yeah. Dan Port's on the Zoom call, so he'll take all the hard questions. I'll take any easy questions.
Thank Rick for making the presentation, very good one. So I've seen a lot of people making picture. Maybe the same people have questions, like for Rick. Very good. Luciano, right?
Hi, Rick. Thanks for the nice presentation. I wanted to know if, besides source code, you also have in this project other types of artifacts that you have to consider doing the maintenance.
Yeah, I'll turn that one over to Dan. Did you look at other kinds of artifacts?
Hi there. Aloha, everybody. Can you hear me?
Yes. Yes.
Is that? Am I audible?
Yes. Yes.
Okay. Yes. I mean, of course, we focused on cyclomatic complexity because of the policy, and had to figure out whether, it was worth following or not. But we've looked at other things like comment density, and see what else other than comment density. Comment density and some other things that we also found had strong correlations to maintenance risk.
There's another question.
So the answer is yes, but not that much more.
Hi, thank you for the presentation. It is Volkan Salmo from European Space Agency. I assume this is a McCabe complexity, right? What is your complexity metric? This is McCabe.
Oh, McCabe, yes.
McCabe.
Yes.
And is it for the C language or?
It was the code was all written in C++ and Python.
Okay, and both you have a 16 threshold for both Python and C++.
That's my understanding of the policy. Is that correct, Dan? It's the same complexity measure irrespective of the language?
Irrespective of the language,
Yeah.
it was completely out of the blue.
Yeah.
Just 16. Doesn't matter what you're writing.
Yeah.
We didn't believe it either, to tell you the truth.
Yeah,
we were like,
same.
yeah, we were like, this can't be right.
Okay, and also 16 is quite a high number, right? If you look to the C code and C++, yeah, it's basically not readable code.
Yeah,
If it's
that's right. 16 is already a high number, but obviously lower is better, right? That's what the graphs showed, but there has to be a threshold somewhere, and that was the threshold that they chose.
Okay, sorry. I am also wondering, do you have other complexity metric than McCabe for the source code?
Other complexity metrics other than cyclomatic?
Yes, because we are also discussing this a lot without industry, and it is very difficult to convince them for the McCabe.
Yeah. No, we had our hands full already with just this, but I think we're considering looking at other metrics. It's kind of difficult because many of the metrics are language dependent. So
There is one that
at least cyclomatic complexity has the virtue of being somewhat language independent.
Okay, thank you for the answer and for the people making the questions from the session. Thanks, Rix, again for presenting.
This is Johannes from Microsoft Azure. So today I will talk about Aegis, which is an analytical service for attributing change impact across computing layers and service components for Azure control plane. Now this is a joint work with my collaborators and colleagues Ken, Yasisa, Minhua, Morelli, Qingwei, Yingno, and Domei from both Microsoft Azure and Microsoft Research. So for this talk, we will start with the background of Azure computing architecture and its control plane. Now, following that, we will cover the motivation, the challenges, and our solutions in developing Aegis. And after the system design, we will end the talk with some performance evaluation results of Aegis. So a modern cloud computing system like Microsoft Azure employs a complex infrastructure to meet the diverse needs on resources from our customers. Now, the top left panel shows the interactions of various components from Azure computing architecture. Component here can be thought of as loosely coupled microservices for maintaining certain cloud resources. Now, the top left panel shows the interaction of various the global service like Azure resource provider, also called ARM, interacts with regional and zonal resource providers to manage cloud resources for customers. For example, to create a virtual machine or allocating computing resources, the ARM would interact with CRP, which is called a compute resource provider, to process the client requests and further interact with other components through API calls. Now, the components that manage the infrastructure and provide the interface for their functionality essentially constitute what we call a control plane. And the bottom left table here, characterize some of the control plane components into regional, zonal, and cluster level services. Now, below the control plane at the node level, a data plane is made up by various agents running a virtual machine hosting environment. So on such kind of interconnected system, implementing change on one component may impact other components, sometimes even across computing layers. Now, a challenge arises from correctly attributing the service quality degradation to a control plane change, and also sometimes people want to infer the causality between the two. And for context, let me first provide some clarity over some of the key concepts here for change events on control plane. So first, a deployed change can be a regular code release, a one-time of bug fix, or a configuration change. Now, these changes get deployed continuously and independently by different components teams in Azure to ensure the service productivity and quality. Now, the changes can get deployed to various computing layers, including the regions, the zones, the clusters. And to ensure the quality of the changes, component teams in Azure really follow a safe deployment policy. So common practice include, conducting gradual rollout, imposing baking time between consecutive deployed units, and also, components team may employ monitors to detect abnormal service behavior after a change in the hope that they can capture bad change in time. And finally, I want to highlight the key difference between a Azure control plane and data plane in terms of new deployments. So control plane changes and data plane ones differ by magnitudes of the available instances for quality evaluation. Now, a data plane change typically occur at the node level, and often when change happens, that result in millions of change instances that are ready for quality evaluations. However, by contrast, a control plane change often occurs at region or zonal levels. For regional change, there are Azure currently has around 50 plus regions over which a monitor can evaluate the quality of a change. So different attribution models are required for Azure control plane and data plane changes. So AGIS at its core is a global domain knowledge-driven correlation and impact assessment engine for Azure control plane. What it does is it cross-correlates platform reliability and latency signals measured from fleet-wide scenario workloads with control plane components change. And for those suspicious component changes, it alerts the corresponding components team. And for those really bad ones with high customer impact, it can trigger auto stop so that it controls the blast radius of a bad change. Now, this AGIS work was motivated by some gaps that we identified in the existing component level monitors on Azure control plane. For example, the first gap is a lack of cross-component correlation. Now, we include a real example here where a network resource provider or NRP introduced a change which eventually led a partition down and impacted compute resource provider or CRP. Now, the existing component level monitors cannot really connect the dots between the NRP change and CRP service degradation because of the lack of a cross-component correlation. The second gap is a lack of a cross-computing layer correlation. Because of the complexity and interconnected nature of Azure system, one component's defect change may interrupt the other dependent component service, where the two components may not necessarily operate and reside from the same computing layers. For example, a bug in the regional CRP service may cause a zonal level failures for zonal components. The third gap is a mechanism. It's a lack of a mechanism to quantify the impact of a bad change to our customer. So when bad change gets caught, we need to answer questions like, what is the customer impact from this bad change? And how much more impact would have been there had this bad change continued getting deployed? Now, the gaps exist between the engineering side and our customers for understanding the impact of the same change. So we need to develop a impact evaluation model to answer this question from the customer's perspective. So we encountered mainly 4 technical challenges in developing AGIS. Now, these challenges range from a proper handling of concurrent deployments to cross-computing layer attribution to effective ways of ingesting domain knowledge into the decision-making process. Now, in the next few slides, we'll go through these challenges and our solution for each one of them. So our first challenge is the presence of many concurrent deployments across components teams. Now, when many service components are involved, concurrent deployments become a challenge for system-wide correlation to correctly attribute a service quality degradation. Now, naive correlation would simply fail because for any spike of fault or latency, there is some change right before it for it to be correlated with. Now, in the bottom left panel here, we showed 2 histograms of those weekly deployment or change volume at the region level for 8 control plane components over a period of a couple of months. Now, the regions have been grouped into Canary region, which is a production environment in Azure from the top, and the production environment, which is from the bottom. Now, the contrast is pretty clear that the Canary environment received significantly more changes than the production environment did. So our solution to this concurrent deployment has twofold. First, we develop a temporal and spatial correlation algorithm to get region-level correlation with high recall. Now, without going into the details, this correlation algorithm evaluates the fault relevancy, fault prevalency before and after a change to a, for example, region, and also across deployed versus undeployed regions. The output from the correlation algorithm are a set of measurements of the strength of relevancy between a change and a platform anomalies. In order to boost the precision, we consolidate those build level decisions across the regions, which is the second step here. Now, the rationale here is, for the same set of candidate component changes, their pairwise order gets shuffled in different regions because components team practically deploy independently. Now, this randomness that is introducing this pairwise order allows our model to surface the right build to attribute a go or no-go decision to. A no-go decision basically means we think this build is bad, we don't want deployment to continue. You guys should investigate before releasing the build to future regions. Our second challenge is the need of correlating change and platform anomaly from 2 components that are from different computing layers. For example, correlating a zonal service change with failures that are measured from a regional service like CRP. Now, our solution also has 2 folds here. First, we can decompose fault signals from a higher level, higher layer components into the granularity of a lower layer. Now, an example here is, decomposing those regional CRP failures into the zonal ones before correlating with the zonal service change. There are some cases when decomposing platform signal is not really feasible. As an alternative, we can project a lower layer component change to a higher layer. An example here is, projecting a zonal service change to region level before correlating with this zonal CRP failures. So the third challenge is about reflecting domain knowledge into the entire decision-making process. Now, domain knowledge may sound heavy loaded, but in our practice, domain knowledge is about having a good understanding of how Azure cloud computing system works. It's about effective abstraction of such kind of domain expert insights and reflecting such kind of prior knowledge into the machine learning model that we built. So in Aegis, we allow contextual ingestion of domain knowledge through both the correlation stage and the post-validation stage of our decision. So I'll be brief here, but basically when we do correlation between a change and platform anomaly, we maintain a weight table to reflect the fault relevancy, the relevancy between a failure signature and a particular component. At the example showed here, we assign higher weight for fault signature that indicate network issues to a network components like NRP, which is network resource provider. And also for failure signature that may often indicate code bugs like null reference exception, we also assign them a higher weight to magnify their contribution to the final decision. In the post-validation engine, we also compare our decision with some known noise signals like fabric failovers and drills. That is a effective approach to reduce false positive decisions. So all these efforts contribute to the quality of our no-go decision, so that our decisions not only make sense from a machine learning standpoint, but it's also correct in the setting of Azure. So our last challenge comes with the innovation need for quantifying the impact of a bad change to our customer. So for that, we develop a impact assessment model using hypothesis testing and a counterfactual analysis to give an overview of how this model works. For deployed regions, the model calculates increased failure rate because of the bad change. We conduct hypothesis testing to keep those failure rates that are statistically significant, and then project such kind of a delta into the undeployed region using a counterfactual projection model. So by tackling those technical challenges, we develop Aegis into this end-to-end analytical service for attributing control plane change impact to Azure for Azure control plane. Now here's an overview of the system design, but basically, AGIS has 5 subsystems, starting with the signal collection of thoughts and change signals from various cans. It then invokes this correlation engine to conduct this many-to-many system-wide correlation. Now, the output from the correlation engine get passed on to the validation engine to validate its decision with known noises and other auxiliary signals. And then also a impact evaluation engine to evaluate the customer impact. Finally, the action engine executes upon the go or no-go decision in the form of alerting components team or automatically stop the bad changes. So this is the last slide. But basically, AGIS has been running in Azure production for the last 6 months. It covers more than 12 control plane components for both their code and config changes. On a typical day, it processes over 1.2 million API call failures to give you a sense of its scale. And AGIS covers both reliability and latency metrics that are measured from different granularities, from fleet-wide or customer workloads or scenarios. So AGIS has caught numerous bad changes and stopped many of them to control the blast radius of their impact. We also evaluate the AGIS performance with some holdout data set that are grabbed from our Azure business for a period of 3 months. So over that 3 months, there has been over 60 unique build versions getting deployed with 700 plus deployment instances to both regions and zones. AGIS on them achieves 80% precision recall. And also, to evaluate the effectiveness of different parts of this subsystem into the final decision quality, we show that the precision would decrease by 28.6% if we remove this post-validation engine, because the post-validation engine is very important for hold the bar for the false positives, and the precision would also decrease by 37.5%, and recall would almost half if we do not have the proper signature weights ingested into the correlation part. And again, signature weight is our way for reflecting domain knowledge into the end-to-end system. So that's the end for this talk. Thank you so much for your time, and we look forward to your questions.
Thanks a lot. Thank the speaker. So there are questions for the speaker, right? Very good. I like that.
Thank you. Oh, can you hear me?
Yes, I can hear you.
Okay, thank you for your talk. I have 2 questions. The first question is, the AGIS is designed for a single change or multiple change in a time window?
Well, it actually covers multiple changes in a streaming environment. By that we mean when we gather those change from code deployment and config or setting change, we don't just grab the change one at a per time and evaluate its correlation, but we grab changes and code and setting changes from those 12 plus control plane components continuously. And then, there are jobs being triggered for running those correlations and, evaluations and actions continuously. So it's not really, one change per time for this entire process, but, multiple changes, many change to many platform anomaly correlation happen simultaneously.
Oh, okay.
Does that answer your question?
Another question is, if a failure occurs in a system, how can we determine it's caused by change or caused by other reasons like a resource problem or other reasons? Yeah. Right.
That's a very good question. So we do have multiple mechanisms to drive our correlation result into a plausible causality results. Just for answering your specific question about to rule out the resource availability as part of the reason for platform degradations in the post-validation engine, as part of the auxiliary information. For example, we do look for available capacity or resources from a given region or zone before raising an alert for a relevant components. For example, we find in practice that a lot of the some of the allocator service failures is not really due to the bad change from allocator or any other components. It's simply because the corresponding region or zone do not have the proper capacity at this moment. So by looking up for the available capacity or resource, before raising alert, we are able to avoid some of the false positives. That is just one way for controlling the false positives. Does that answer your question?
I cannot answer, but yes, I think she's satisfied. Thank you again for the presentation and for answering the question. It was a very interesting talk again.
Thank you.
Hello, everyone. I'm Yifan from Peking University and group. I'm glad to present our empirical study on change-induced instance of online service system. My presentation includes 4 parts: background and motivation, methodology of study, result of study, and implications. As shown in Figure 1, the online service system in our group are constructed based on microservice architecture. The system consists of more than 3,000 microservices running on over 1 million containers and serve a billion of users. The workload typically 1 million custom requests per minute. One of the characteristics of microservice architecture is frequent changes. There are tens of thousands of changes per day in the system due to software deployment. Such frequent changes are likely to induce incidents. In online service systems, an incident is any unplanned interruption or performance degradation of a service that is causing custom impact. Change-induced incidents are the incidents caused by engineers' changes to code, confusion, and the environment of service. The life cycle of the change-induced incident is summarized in Figure 2. Change management is a process of preparing a change, checking the risk of inducing incidents, deploying the change, monitoring system status, and diagnosing change-induced incidents. A typical workflow of change management in our group is shown in Figure 3, which consists of 6 stages, including change preparation, pre-change checking, change deployment, post-change monitoring, change incident diagnosis, and change incident resolution. In order to enforce changes with minimized negative impact, change management has been applied in industry. However, change-induced incidents are still happening. In this paper, we conduct the first empirical study to characterize the change-induced incidents and identify changes of change management in practice. Specifically, our study aims to answer the following request questions. What is the severity of change-induced incidents? What are the characteristics of change-induced incidents in terms of change time, root cause, and mitigation strategies? What are the change management challenges in practice that lead to interruption, failure, and delay in mitigation? We believe our work could help understand change-induced incidents and give some guidance for research and engineer to improve change management. For the methodology, we collected 161 change-induced incidents over 2 years from real-world large-scale online service systems in our group as our study subjects. 2 authors spent 3 person-months analysis these incidents manually in terms of their severity, turn times, root cause mitigation strategies, and changes of change management with the following procedure. 50% of these change-induced incidents are randomly sampled for pilot labeling. The remaining 50% 50% instances are labeled based on the schema generated in the pilot labeling for reliability analysis. Then I will talk about our study result. The result include 3 parts. Firstly, I will introduce the incident severity and then talk about the characteristics of change-induced incidents. Finally, report the key changes. To answer RQ1, we collect another 158 non-change-induced incidents and compare with change-induced incidents in terms of severity level and incident resolution time. We can find that change-induced incidents have higher severity levels in the overall distribution and more resolution type than non-change-induced incidents. Well, we classify change-induced incidents into 5 categories based on their change objects. We can find that most change-induced incidents are induced by code change. Each report contains a detailed description of the root cause. From these descriptions and engineers' discussion, we identify the root cause and categorize them into 6 types. We can find that although more than half of incidents are caused by code defect, 40% of incidents are caused due to non-code related issue, which can be avoided by careful change operations and effective pre-change checking. Similar, each report also include a detailed description of the mitigation strategies. From these descriptions, we identify the mitigation strategies and categorize them into 5 types. We can find that rollback is the most popular mitigation strategies, a strategy for each type of change-induced incident. What's more, mitigation via rollback, node reboot, and traffic switch account for more than 70% of incidents, which indicates that mitigating incidents automatically is possible for most change-induced incidents. Finally, change management runs through the life cycle of change from pre-change checking and interception to post-change diagnosis and mitigation. However, there are still many instances escaping from early checking and interception, and some instances take a lot of time to diagnose and mitigation. Similar, incident report usually contains the reason for interception failure and delay in mitigation. From these descriptions, we identify 4 practical change management changes which require new technique to solve. Here, I only talk about the change of low business traffic. Other details can be found in our paper. For the change of low business traffic, post-change monitoring in change management relies on real-world business traffic to find issues hidden in changes during deployment. However, business traffic necessary for triggering issues in changes can be low or even absent in some scenarios. When this occurs, it becomes difficult to find hidden issues during post-change monitoring. On the one hand, issues that only occur in particular scenarios cannot be triggered when required business traffic is is absent. For example, Figure 11 presents a case showing an incident without any anomalies during post-change monitoring due to the low business traffic. On the other hand, even though issues can be triggered, the slight fluctuation of monitoring data makes it difficult for managers to detect anomalies. Based on the above findings, we point out 4 practical implications. Here, we introduce the implications of simulation environment construction. The simulation environment can simulate the production environment and replay online traffic. Deploying changes in the simulation environment to check whether unexpected behavior are observed before deploying in the production environment may be an effective way to solve the challenge of low business traffic. Finally, let me conclude my presentation. We conduct the first empirical study on change-induced incidents based on 161 real change-induced incidents from a large-scale online service system in our group. And then we identify 4 vital change management challenges in practice. We also present representative real-world cases and statistical evidence for our findings. Finally, we propose 5 practical implications for engineers and researchers, which shed light on future research and engineering efforts to enhance change management. That's all. Thanks for listening. More details can be found in our paper.
Okay, let's thank the speaker, Tufan, which already got a question.
Hi, thank you for your presentation. So in practice, I noticed that the labeling of incidents can be quite of varying data quality. So what I was wondering is what kind of data pre-processing did you do to get to these final cases? Like, did you need to do maybe some filtering of duplicate incidents?
Your question is how we collect the data?
Yeah, how did you get to these final 160 change-induced incidents?
Okay. After each incident have been mitigate, the incident will record in the database. We collected the 161 change-induced incidents from the incident database in our group as our study subjects. These change-induced incidents are identified by engineers. After successfully mitigating an incident, the engineer will analyze the incidents and submit a report recording detailed information such as the root cause. If the incident is instanced by a change, engineer will mark the incident as a change-induced incident and attach the change ticket.
Okay, thank you and for the introduction and good afternoon to everyone. I'm glad to be representing my colleagues at the Institute of Software Systems Engineering at Johannes University, Austria. And in this paper, we had a collaboration with our industrial partner from Flanders Make, which is a Belgian research institution. And And let's talk about the industrial needs that we are fulfilling in this work. And to do that, I'd like to introduce an example, industrial scenario that was provided by our partner. And in this scenario, we have a team of engineers collaborating to develop software components for agricultural machines, since this industrial partner works with the manufacturer of these machines. So we have at one side a team of architects, and they're using the Microsoft Visio tool to create design models. These design models are created using the UML. These models include the class diagrams, state machine diagrams, among others, other types of artifacts. And at the other side, we have a team of developers that are responsible for the implementation of these components. And this implementation is done in Java using IntelliJ, the IDE. Now, since this is a collaborative work, the company, one thing that is very important for the company is that the artifacts being developed are consistent between each other. Now, consistency is a word that you're going to hear a lot during this talk. So I think it's important to clarify that this consistency in this scenario corresponds to artifacts fulfilling specific quality constraints to assure their quality. One example here, a simple example, is that all the elements that are present at one side, for instance, you can see the vehicle configuration UML at the top, and this class and the elements from this class should be implemented in the corresponding Java. So all the fields, all the methods, etc. Which means that if a change happens at one side, the artifact at the other side is now inconsistent because something is missing. And what the company currently does is the engineers have to manually check the change that happened and see the artifacts impacted by this change and which inconsistencies were introduced. Now, this is a manual consistency checking, as we call, and it has some problems, such as it takes some time and effort from the developer or the other engineers that can be used in the implementation. It is also an error prone because it relies only on the knowledge of these engineers. Furthermore, the company has no control about when the engineers are going to perform this checking. So they can delay to later steps of development, creating cascading problems in the artifacts. Now, in this scenario, we had only two tools and two types of artifacts, but in reality, the companies will deal with multiple types of artifacts and multiple tools. For instance, the SolidWorks for creating the schematics of the mechatronics components. And this means that whenever one change happens, as simple as it is, it's the responsibility of the engineers to go through all these artifacts to find the negative impact that these inconsistencies may have. And this, of course, escalates the previous mentioned problems. And it's more likely that these inconsistencies will not be found at all. So we sought in literature to see how we can solve these issues. And we have used here two system mapping studies to identify limitations of current approaches in this field. For example, we found out that most approaches focus on single type of artifacts, which means that they are not suitable to a multi-domain environment such as the one I presented with multiple tools being used. Also, most approaches apply the checking their own tool, and this would require the company to change the tool set being used, and changing the tool set might disrupt their development lifecycle. We could also look at how automatic generation can be done. For instance, we can automatically generate the source code from the UML. To do that, however, some revision and supervision is also required, and some approaches would also require additional steps in the development lifecycle, also the introduction of additional tools. So based on the limitations and the problems I mentioned, we defined the requirements of our solution. And the first one is to support the consistency checking for multiple types of artifacts. And to do that, the checking should be customizable. So in case the company wants to introduce new tools in their lifecycle, the approach should be able to be applicable in these new tools also. We also should provide instant feedback about the consistency state of the artifacts. And this is achieved by triggering the consistency checking whenever a change happens in any artifact that is part of the project. Another very important requirement is to avoid disrupting the current development lifecycle of the company, which means that we shouldn't ask the engineers to migrate to a different tool. They should keep using the same tools they already use in the company. So the solution proposed, it's divided into two phases. The workflow is divided into two phases. So we first have the preparation phase. And in this phase, we connect the tools to the approach, which is running in a server that provides a collaborative infrastructure. And this is achieved by implementing two adapters to the tools that the company uses. And these adapters allows the engineers to connect to the server. Once this connection is achieved, the approach will generate traceability links. And these links are there to connect the artifacts that come from different tools. For instance, we can now connect the Java implementation with the UML design models. And this connection is important because on the next phase, we have the consistency checking being performed. And we have the definition of the consistency rules. And in this study, we have used the object constraint language for defining the rules. And these rules are applied to the artifacts that are now connected to the server. And whenever a change happens, the checking is triggered and the rules are applied. And through the use of the traceability links, we can identify if two or more artifacts are inconsistent and retrieve this information to the engineers. Now let's take a look at how the approach looks like on the previous presented example. So the first difference here is that we now have the design space infrastructure as part of the environment. And in this infrastructure, we have defined a consistency rule. Now, as I mentioned, the rule is defined using OCL, but for the sake of simplicity, I only keep a natural language representation of the rule here. So the rule says that all properties from a UML class must be implemented in Java. So the tools are connected to the approach or the server, and the trace links are generated. And here we have the traceability links between the artifacts from UML and from the source code Java. So now the change happens, and the difference here is now the approach doesn't require the engineer to do a manual check, because we would automatically identify the change, and through the trace link, we'll analyze the impacted artifact. And in this case, would be done a comparison between the fields of the UML class and the fields of the Java implementation, and we'll find out that one field is missing, and this inconsistency will be retrieved to the engineers in their own tools, so they don't have to use a separate tool for that. For example, in IntelliJ, the engineer can receive a warning or even an error message. It's customizable to their desires. We have also performed a scalability evaluation using 6 open source Java systems that contain UML documentation. And we have applied 28 consistency rules to check the inconsistencies of these systems. And the results, a lot of numbers here, but the important part is that we are able to apply the approach in larger systems with up to 18,000 elements on the source code side and 9,000 on the UML side, and within a reasonable amount of time. And further details are available in our repository online. So to conclude this talk, I would like to mention that we were able to achieve our goal of proposing an approach that finds inconsistencies across multiple types of artifacts. And this is done by using the traceability information between the artifacts that are being analyzed. The approach can reduce the time and effort spent in the consistency checking, because no longer the engineers have to do this manually. The checking is performed after each change, which means that the engineers receive instant feedback from the consistent state of the artifacts, and they can decide what to do with this feedback. They are also notifying their own tools, which means that we can the approach is able to preserve the development lifecycle of the company. They don't have to integrate new tools or learn to use new tools. So with that, I'd like to thank you for your attention and invite you, in case you're interested, to check it out, our approach documentation, and we also have a video showing this example I demonstrated. You can also contact me afterwards. Thanks.
Thank you, Luciano. Thank you. So, any question in the audience? Don't be shy. It's been a very nice talk, I have to say. I was impressed. You did not only go in industry, but also analyze open source data. So it's quite. Thank you very much, by the way.
Thank you.
From a practical perspective, it's a side paper, and you demonstrated your tool has, applicability in the Java domain, in the Java language. How, your results are confined to that language. Can you, apply them to other languages or in another domain? Have you seen ROS? Usually it's in C, C++, for example, most of the languages. So maybe you have any thought about that?
So in this, we decided to use the Java open source systems, but the company also has different types of artifacts. In the paper, we also describe these other types. And the only requirement so far to apply the approach in C++ or C# is that tool that supports, or the IDE that supports that language needs this tool adapter to be connected. And we have other, in the website of our institute, we have other examples where we have used approach even with Excel or, as I mentioned, I think SolidWorks already. And we are currently also working with Visual Studio and other tools to expand the range of the applicability.
Thank you very much. I mean, it's impressive work already doing in a language, but moving on is even more. Thank you very much, really.
Okay, I'm going to present the collaboration of the WordPress platform and its plugin. Does it work? No? No? Oh, okay. Okay, sorry. And so WordPress dominates the content management system market by 64%, and WordPress is a plugin-based software ecosystem, which means there is a platform that could be extended by a set of software projects, which we call plugins. And these plugins rely on the platform to provide resources such as data, libraries, and these plugins cannot be used without the platform. So which means there is a high coupling relation between the plugin and the platform. And because of such system architecture, there are more than 54,000 packages, plugins are available in the WordPress ecosystem, which gives users a wide variety of features to build their own websites. However, because of such architecture, 99% of the plugin actually had at least one urgent release that is released within 24 hours of its prior release. And the most common reason of this kind of urgent release is because of the incompatibility issue between the plugin and platform because of the software system architecture. So we identify the three types of plugin releases that plugin used to react to a new version of WordPress, which are off-sync release, support, and in-sync releases. So as we could see in the plot, when WordPress releases a new version, for example, 4.8, and a plugin will release a support release after a certain period that clearly support WordPress version 4.8. So any releases between the WordPress 4.8 and these support releases are off-sync release, which means these releases are not officially support version 4.8. And any releases after the support release and before the next version 4.9 are in-sync releases. So we study the co-evolution of the WordPress platform and its plugin by the following three research questions. So when do plugins support a new version of WordPress, and how do they support a new version of WordPress? And also how do these plugins co-evolve together? And so for when do plugins support, we observe that plugins supports a new version of WordPress after a median of 38 days, and with a lag of just one release behind the latest available version of WordPress. But as we could see from this plot, actually 38% of the plugin actually release a support release after more than 2 months. And the median lag of the release of 38 days actually is inconsistent even for the same plugin, which means one plugin might release a support release like within 7 days after a new version, but sometimes they might release that after 2 months. For the second article, we studied how they support a new version of WordPress. And we observed that 89% of the plugins actually at least one off-sync release. And every plugin have at least a median of 6 off-sync releases, and 31% of these off-sync releases are made within 1 week after a new version of WordPress, and 70% of them are made even after more than 2 months. And these off-sync releases are risky because they are more likely to be followed by an emerging update, and compared to the other in-sync releases. So the final one article studied the co-evolve among the plugins themselves. So we observed that plugins have a median of 6 peer-triggered releases, and the change in these peer-triggered releases were according to a median of 5 other plugins. And because peer trigger releases are not expected by the developer, because plugins are designed to extend the functionality of the WordPress platform, but because of the system architecture in the WordPress software ecosystem, plugins may implicitly or explicitly depend on each other. So we studied the reason why they kind of have this peer-triggered releases, and the most common goal is to fix incompatibility issues between peer plugins, which accounts for 46%, and sharing resources such as data workflow or even layouts is the common reason responsible for the incompatibility issues. So in conclusion, we studied how plugins react to a new version of WordPress, and we found plugins support a new version in a median of 38 days. And the off-sync releases are actually risky than the others. And peer trigger releases do exist, although like developers didn't expect that. And thanks for your attention.
Very good. So I guess there is a question. Yeah, I was expecting it. Very good.
Thank you very much for the presentations. I have been working with WordPress, so I know that there is a mess with these many plugins and stuff. But I was wondering, because I think that when the co-evolution happens after the release, it's a lot of effort to get back and check what is the problems and do a lot of works related to that. Is there any recommendation for the development time to double check if some potential problem will happen or something like that, like be more proactive than reactive regarding these potential problems?
I assume that your question is related to plugin developers, right? Yeah. Yeah. In that case, I would suggest at least to check the best practice suggested by the WordPress, because actually the result we had right now, like this compatibility issue and sharing resources issue, WordPress already suggests some kind of best practices, and developer didn't read that before deployment or implement. So somehow they kind of have certain these incompatibility issues between them, and this kind of issue they might use some tools or like build some kind of for example naming checking or like library checking, because as I know certain library, if you load twice, and then they might cause incompatibility issues, and you might need to either remove the loading library in your plugin, but maybe another plugin also remove that, then you still have another issue raised. Yeah, so it's more like nested structure because of it's a plugin-based system. Yeah, thank you.
Well, thanks for the presentation, Justina. So I think we can, thank the speaker.
Thank you.
Okay. Good afternoon, everyone. So I'm Ely from NTU Singapore. So here today I'm going to present our general first paper accepted earlier this year at Tufan. client-specific upgrade compatibility checking via knowledge-guided discovery. This is a joint work with UT Austin and Meta. So to upgrade or not to upgrade, that is the question. Compatibility issues are not new, so they can be caused by evolution of software libraries. A recent study shows that 50% of the study project breaks after an upgrade of some libraries. And 40% of these issues are actually runtime errors. So they cannot be simply caught by just rebuilding or recompiling the project. Therefore, developers often try to avoid upgrades of the libraries because it causes too much trouble. In another study, 82% of developers say that they keep outdated dependencies. However, not applying upgrade may cause some other issues, such as security concerns. Right? So what do we do? So to make it even worse, these compatibility issues are often client-specific, meaning that the same upgrade of the library may be fine for some client, but it may cause issues for others. So here is an example. So the library code here takes two input strings, S1, S2. It will return an empty string if they don't share any common substring. Very simple. And the upgraded version will return a null pointer instead. So as you can imagine, right, this will cause some issues if you don't account for this null pointer returned in your client code. So for example, this client 1 on the left may throw some null pointer exceptions after this change of the library. But on the other hand, right, this client 2 on the right is totally not affected by this change because the input passed to the library API will always share a common part, ABC. Right? So this is what I mean by client-specific incompatibilities. So we really need to consider how the library API is used in a particular client in a case-by-case manner. So our proposed solution to this is called CompCheck, client-specific compatibility checking. And there are two main components of this, knowledge mining and incompatibility discovery. Right? So in knowledge mining, we try to build up a knowledge base of previously discovered incompatibility issues, namely a client test that passes before the library upgrade and fails after. Right? So for example, this test here fails because of an API call read object. Then for each arguments passed into this problematic API, we record its execution traces and intermediate states. And in this example, all these three arguments are very simple. They are just instantiated within the same method, and it didn't go through any other operations. So the traces also look very simple. But in other complicated cases, the trace can be longer. So we use this to represent the client context of the given incompatibility. Next, when there are multiple failed clients because of the same API, we can then merge their context together to get a more compact summary automata. And this is stored in the incompatibility knowledge base for later use. Later, when there's a new client project and we want to decide whether there's any incompatibilities, we will first analyze its usage context statically. And if our analysis thinks that this client context looks similar enough to one of the knowledge stored in our knowledge base, then we'll try to trigger this incompatibility by generating a test case. So normally this will be very challenging, right? To generate a test case automatically, if it requires some very complex objects, then it may not be possible. But luckily, we have those intermediate states and objects stored in our knowledge base, so we can try to reuse them as much as possible in constructing these test cases. Yeah, for example, we take a state and then just reuse it in our test. So we evaluate our tool on a set of popular open source Java projects and libraries. And we build our knowledge base on a subset and then use our tool to try to identify similar issues on the rest of the data set. And we compare with three baselines. One of them is called Sensor, published earlier in TSE. So they target a very similar problem. Instead of looking for semantic differences caused by library upgrades, they are looking for semantic differences caused by so-called library dependency conflicts. Namely, when you put two different versions of the same library on the class path, it may cause some behavior conflicts. Right? So we could compare with them after some minor changes to the tools. You may refer to our paper for more details on the comparison and other baselines. So in terms of incompatibility discovered through the generated tests, our tool is more effective, finding 70% more problems than Sensor. And we also found that by reusing objects stored in our knowledge base could largely improve the success rate in test generation. So both our tools and dataset are available online. You're welcome to try it out and use them in your future research. And that is all. I'll leave the summary here and happy to take some questions.
So thank you, Lee. So there is a question here for you. Right, over there. Thank you. So I can move a bit, do some sport on the way.
All right. Thank you for the talk. I'm not sure if I understood this correctly, but like you're looking at many similar failures and trying to like get knowledge out of that to save for future failures, right?
Yeah.
So have you noticed like that some are more common? Like for each kind of piece of knowledge you store in the knowledge graph, right? Or in the knowledge database, like what is the frequency? How often do you see enough of something to be able to distill knowledge from that? I don't know if you have statistics about that or not.
We haven't counted that. So you just trying to see if there's any patterns or?
So would two, like if it occurs one, does it go into the knowledge graph or like knowledge database, or is there at least two occurrences? Like, is there any minimum times you see something?
For any of the failures we've discovered previously, we will add that into the database. But this database is also dynamic. So
it's evolving.
Yeah, when you discover new, you add it back.
I see. Okay, thank you.
Thank you, Sarah. Okay, good. Any other question? Maybe I will have one, but just more out of curiosity. You mentioned in the beginning of the presentation that, inconsistency can lead to security aspects. Did you investigate that, or are you going to investigate that? I got curious, since you mentioned.
We will investigate that. Actually, what I'm trying to say is that if you don't upgrade, then there could be a security concern because there could be some vulnerabilities not being fixed in time. Yep. But if you upgrade, then it may cause some incompatibility issues. It's kind of a hard choice, but we try to build our tool to make this easier. Yeah.
Okay. Thank you. So let's thank again the speaker. Thank you. Very nice slide, by the way.